Hello. Okay, so here we're going to talk through global climate change. For this section, we're just going to present a basic introduction to the issue of climate change. What are we going to do in this section? First, we'll talk about what is climate change. Then we'll talk about some of the drivers of climate change. We'll look at the implications of climate change, and then ask the question, why is climate change so difficult to solve? Finally, we'll talk about the role of business. So undoubtedly, many of you are already very familiar with climate change. The greenhouse effect is driven by increasing quantities of carbon in our atmosphere. The reason this is an issue for us is because carbon traps heat from the sun in the atmosphere. Obviously, this is good for us. It creates an atmosphere and a climate that's actually useful for humans. We can live through it. However, if we end up having too much carbon in the atmosphere, we can trap too much of the sun's heat in our atmosphere. We can warm up the atmosphere and change our climate relative to what it has been in most of the history of humankind. People often ask, is this any different? Has anything changed? If we look back a long time period, and we're talking 600-some thousand years across the time period in which we're able to actually determine what concentrations in the atmosphere of carbon have been, we can see that carbon has fluctuated relatively significantly over time. If you look at the left-hand axis, this is parts per million, basically the milligrams per liter, so it's a concentration of carbon in the atmosphere. So concentrations have fluctuated basically from, 175 or 200 parts per million, or milligrams per liter, up to about 300 parts per million over the last 600,000, practically a million years. Obviously, what's interesting to us today, and what's potentially problematic for us today, is that carbon concentrations today have risen well above 300 parts per million, well above the historical norm, and now they've exceeded, this map is a little bit old, 382 parts per million. Today, they've actually exceeded 420 parts per million by 2019, where we are today. So we see a significant increase in carbon relative to this long historical time period. Data from ice cores in the Antarctic, I should say, and from lots of glaciers on mountaintops and other kinds of places have allowed us to not only determine this historical record of carbon concentrations, but have allowed us to determine the historical record of temperatures. So we've been able to recreate these temperature distributions over time, and we can see that temperatures have been correlated in general with carbon in the atmosphere. So there's very little doubt that carbon in the atmosphere and average global temperature are relatively well correlated over time and move together over time. Hence the concern today that increasing levels of carbon above this 400-some parts per million that where we exist today could have very important and large impacts on the climate that we have gotten used to. As we think about what drives climate change, there are lots of factors, obviously. Fossil fuel burning. Let's look at this figure on the left. The figure on the left shows the annual anthropogenic carbon dioxide emissions and partitioning of that carbon dioxide emission into different areas. So the top half of this graph is the emission. The gray area is the emission of carbon dioxide from fossil fuel and cement burning. These are data from Energy Statistics, and it tells us the annual amount of this carbon emission over time. The brown area is the carbon emission due to land use change. This is an estimate of the amount of carbon that has been emitted by converting forests into agricultural land. This is a process that's been going on for at least hundreds of years, and the amounts have risen from, less than 1 billion tons of carbon per year to above 1 billion, almost 2 billion tons of carbon per year over big chunks of the last century, the 1950s and 1960s, as we took enormous amounts of land from the tropics out of forests and into agricultural land uses. The area and the amount of deforestation that has occurred in the last couple decades has declined, however, although this number remains at about 0.8 to 1 billion tons per year, or petagrams. So the total amount of emissions per year is above 10 petagrams, or billion tons per year, and it's a combination of fossil fuel burning and cement emissions and land use change. This carbon has to go somewhere. It goes to one of three places. The green area is into a sink called forests. So this is a sink of forest growth in some part of the world. So some of this carbon from the atmosphere is moved into biological material that's growing on an annual basis. The lighter blue area is the measured atmospheric growth rate, so it's the increase in carbon in the atmosphere. So this is the part we worry about. This is the part of carbon that is increasing in our atmosphere, and it's the part that actually causes climate change. The other part of this carbon that we emit every year goes into the oceans. This part we also worry about. It's the part that causes acidification of the oceans and potential damages in the oceans due to increasing carbon levels there. It doesn't harm our atmosphere, however. So the carbon that goes into the atmosphere goes into three places. The part that goes up has to be balanced by going into one of these three pools, if you will. And one of these three pools is a pool that will contain carbon in the future, either in biomass, which is the green area, so that's living material, trees, crops, wetlands, other kinds of places where carbon can be stored on the landscape. This is the atmosphere portion, and this is the ocean portion. It's roughly a third each. However, the one that's growing the most is this biosphere. As we look at the biosphere, we can see interesting things happening in the biosphere over time. So look at the increase in atmospheric concentration since 1950. This is the famous Keeling curve. The Keeling curve is something that was shown by scientists in Mauna Loa, at the observatory on Mauna Loa in Hawaii back in the 1960s. And basically what they noticed was that there was an annual cycle in carbon, up and down, up and down. Every year it went up, every year it went down. And they were able to show that the reason for this increase in carbon and decrease in carbon on an annual basis, even though the long-term trend is up, is due to the growth of trees in the northern hemisphere. So in the spring, the amount of carbon in the atmosphere would decline by the amount of carbon that grew in trees. In the fall, the amount of carbon would increase as there wasn't any growth in trees and emissions continued down their traditional path. Carbon dioxide is increasing because we're emitting two sources of carbon, carbon from energy emissions and carbon from land use change. It's increasing because only some of it makes its way into green growing material, and only some of it makes its way into the ocean, and the rest makes its way into the atmosphere. And this part that goes in the atmosphere is what's causing the warming trend. There are questions about whether the Earth is warming. Many people have asked, do we really detect a signal of change in terms of warming? And data for this does suggest that we are seeing an increase in temperatures. So the figure on the left is a famous figure from Michael Mann at Penn State University. It's a figure he first presented in 1998, and what he showed is that temperature levels are at their highest levels in the last 1,000 years. So temperature levels are well above what they've historically been over a 1,000-year period. And what's important about that is to recognize that, the question is why is it interesting that temperatures are increased? Haven't they increased and decreased over time? This figure shows that absolutely they've increased and decreased over time. They've increased and decreased over time with lots of different factors: sunspot activity, distance of the Earth to the sun, different kinds of processes within the Earth, often having to do with ocean currents and shifts in ocean currents. But if you look at this and you see these uncertainty bounds sort of along this, you can see that the temperature increases that we've observed are not only above historical norms, but well above and statistically above what we might have expected being an anomaly that could be explained by something other than climate change. So the point of this figure is to say that, as we look back in time and we look over the historical record where we've got actual data that we can estimate temperatures over time, we see that there's very little doubt that these increases in temperature that we have now are very different from the temperatures we had historically. And there's very little doubt that these temperatures are well above the temperatures that we would have had historically. We have lots of good data now suggesting that temperatures are well above where they should have been if we had history to go by. And so is this warming due to humans? This is the biggest question that we really have to face with climate change. Is the warming due to humans? Human influence has been detected in warming of the atmosphere and the ocean, in changes in the global water cycle, in reductions in snow and ice, in global sea mean level rise, in global mean sea level rise, and in changes in some climate extremes. This evidence for human influence has grown since the AR4, since the last assessment report of the Intergovernmental Panel on Climate Change, in other words, and it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. Well, it seems stupid for me to have to read that to you, but I read it to you because this is a really important statement. Basically, each time the Intergovernmental Panel on Climate Change gets together and works on their assessment reports, and they're working on their assessment report number 6 now, they seek to answer this question. How likely is it that what we're observing in temperatures is a function of the human influence? The way they go about that is to try to exclude all other causes of potential rises in temperatures. So if we look back at this figure that we saw just a second ago, the point of this is to say, could there be something else causing this increase in temperature rises? So in the last 1,000 years, was there anything we could have seen that would have driven temperatures up to that level? And we didn't see anything in the last 1,000 years that would have driven temperatures up to that level. Are there other things that could have caused temperatures to have increased to that level? Well, here's the final figure, or one of the figures the IPCC uses to ask that question. So basically, the scientists, the atmospheric chemists, and other scientists who work on the atmosphere have tried to put together what they call the relative forcing of each of the gases, each of the things that we as humans put up into the atmosphere. And they also try to account for all the things that are happening in the atmosphere that are not caused by humans. So we know, for instance, if you start at the top of this figure, that carbon dioxide is emitted into the atmosphere by humans. It's also emitted by other kinds of things. And we've been able to figure out what the warming effect of that carbon dioxide is. And that's this bar up at the top. It says that the relative forcing, you don't have to worry about the units over here, but the relative forcing is 1.5, 1.6, somewhere in that range. Okay, so just think of that as a unit. So that's a relatively strong factor, right? Relative to all these other factors. So if it's a factor that has a bar on the right-hand side of this 0 point, it's something that causes warming. If it's a factor that has a bar on the left-hand side, it causes cooling in the atmosphere. So another greenhouse gas is methane. Methane is a shorter-lived greenhouse gas, but it causes warming just as carbon dioxide does. The amount of methane we've emitted into the atmosphere causes relative warming of 1, a little bit less than carbon dioxide, but still nonetheless important. Halocarbons, these are CFCs, these are the kinds of things that we use in refrigerants that get released into the atmosphere during many industrial processes as well as through our refrigerants, is both a warming and a cooling factor depending on where it occurs in the atmosphere. The net effect being that it's a positive warming factor, although it's relatively modest in terms of its total warming effect, about a 0.4 or something in terms of the net scale, in the gross scale, and about a 0.3 in the net scale. N2O, nitrous oxide, is an emission from agriculture typically, but also from some coal-burning power plants. That has positive warming effects, but it's relatively modest as well. Carbon monoxide is positive. Organic compounds, other kinds of organic compounds are also positive. And then nitrates are actually negative. So some of these actually have negative impacts, okay, depending on how they affect the atmosphere. So it's the direction of effect in the particular place that they occur. Aerosols and other kinds of things have a negative effect. So we can see that they have a negative effect on warming. So these are things that are happening as a result also of human activities, of things that occur in deserts that blow sand into the sky, etc. Then there are cloud adjustments. So we know that clouds actually reduce greenhouse gas warming. And so we adjust these, to figure out the relative warming. We adjust this by adjusting the cloud effects. Albedo change is a land use change factor. So basically the reflectance of the Earth depends on how many forests are out there. If we have less forest, the Earth is more reflective. If we have more forest, we have a darker surface, and the Earth takes up and gobbles up more of the sunlight and heats us up even more. So land use change actually has two effects. One is it causes carbon dioxide emissions, and the second thing it does is causes less albedo. Changes due to solar irradiance, that's basically sunspots. Between 1750 and the present, sunspot activity has been positive, but is relatively small. So the net effect of all these activities by 2011 was a 2.2, 2.3. So this is the kind of information the IPCC uses to say that, you know what, most of the things that cause these things to get into the atmosphere, cause these things to happen, are human driven. There are not many natural occurrences of these things. There are some, they're accounted for within the models. However, most of these things are caused by humans, and therefore we can say with relatively strong scientific certainty that most of the warming that we've observed is due to humans.